At your hospital, patient safety events are tracked using monthly net safety events, NSE, defined as NSE equal events at beginning of month plus new events reported minus events resolved or closed. The table at the bottom of this problem contains a record of your hospital's monthly NSE for a single clinical unit over the previous 60 months. Copy this table to cells A1 to D61 in your Excel portfolio. Remember, when you're copying data from a HTML table, you want to copy something outside the table. Submit. It is outside of this HTML table. I'll click copy, and then in A1, I'll right click and then pick match destination formatting. After you copy the data, 13, your number's gonna be different than mine, is in cell D2. And then it says delete columns A, B, and C. A, B, and C, right click, delete. And now you have NSE in cell A1, and then the values of this variable in cells A2 to A61. And we're going to name it NSE. So I'm going to name this NSE. After I type NSE there, I'm going to press enter. Over here, I'll make sure that all the cells are included. I'm going to do that by typing equal, and I get a bunch of functions. These are functions. This right here, white squares with blue squares, this is the icon for a defined object in Excel. An object in Excel can be a set of cells. I named that group of cells NSE. So I'll type NSE, then I'll double click on that. And notice there's a blue box around just the numbers. All the numbers are included in this blue box. This blue box is a set of cells, an object that is named NSE. Next, copy the table below to Excel so that the values of the upper limits are in cells E3 to E10. E3 to E10. Again, when I copy a table in Excel, I want to copy something outside of it. I'm going to copy the word use and everything inside the table. And I want it so that the upper limits are in cells E3 to E10. I need to right click here, put my cursor over match destination formatting. Now the upper limits 5.5 to 30 are in cells E3 to E10. So I'm going to click on that. I'll bring these two down, bring that down. I'm going to delete the word use, double check the last two rows here, 16 and 16. I got 60 observations. Then I want to name E3 to E10. That's E3, that's E10. These are the upper limits of the intervals. I'm going to name these bins, like laundry bins. I'm going to press enter. And then I'll come down here and I'll type equal B. Again, I get a bunch of functions. And then I have an object, which is a named set of cells in Excel. And that named set of cells is bins. If I double click that, you'll see that the upper limits of each one of these intervals is highlighted with numbers 5.5 to 30, and they match these numbers here. I'll press escape and then I'll backspace. Now what I want to do, I want to use this formula here to do what? I want the frequency. I want the frequency of the values of this variable that lie between 2 and 5.5. The first one that lies between 2 and 5.5 is what? That doesn't lie in between 2 and 5.5, but this does. So there's 1. That doesn't. So I have 1. So I can do that by hand, but why should I do that by hand when Excel has a formula that will do it for me? Now, this is an array function. An array function is one where the function puts out multiple values in multiple cells at one time. Equal average is a cell function. Equal frequency is an array function. I want all the frequencies to appear here. So I'm highlighting the boxes that are just to the right of the upper limits of my intervals. And then I'm going to copy this over here. I'm going to come over here and I'm going to paste it right there. And notice what happens when I paste it there. NSE is the blue box. The red box are the bins. And if I press Control Shift Enter, it might be Command Shift Enter on a Mac. When you hold down Control Shift and then press Enter, the frequencies appear. And now there's only one. Remember, we found one of the values here between 2 and 5.5. There are 3 between 5.5 and 9. There are 11 between 9 and 12.5. There are 22 between 12.5 and 16, etc., etc., etc. There's 1 between 26.5 and 30. So these are just the frequencies. The cumulative frequencies are found by doing this. I'm going to start at the very last interval. I'm going to type equals sum, use the left arrow button. I'm going to hold down the shift key. I'm going to go to the very top frequency. So I got F3 to F10. Now here's a trick that you're not going to understand until I show you what it does. I'm going to put a $sign between the F and the 3 because when I copy this formula here, 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 and here, I want this blue box to be frozen in cell F3. But I want this edge of the blue box to move up 1 as I copy this formula to each one of these spaces. And it'll make sense in a second. When I pull this up, watch what happens. It's 59. Why? Because now I'm just summing these values. Whereas down here, I'm summing all of them. If I continue moving this up, the blue box gets smaller, and so does the sum. Now that you understand what it's doing, I can just grab this and do it quickly. So what does this 1 tell us? Well, there's 1 of these values over here that are less than or equal to 5.5. What does this tell us? Well, there's 4 of these values that are less than or equal to 9. 1 of them is in this interval, and 3 of them are in that interval. This tells us there's 15 numbers less than or equal to 12.5 in this set of numbers. Notice that the total for the frequencies is the same as the final cumulative frequency. I'm going to jump pause while I enter these numbers. Welcome back. I entered these values into these boxes and pressed enter, and I got them all correct. Now I'm going to use Excel to do descriptive statistics on NSE. And the way I'm going to do that is I'm going to copy this table and the word use outside this table because I want to preserve the HTML formatting. I'm going to copy that. I'm going to paste it right here. Notice that I give you the function here to calculate the particular statistic for these answer boxes. In order to get them to work, notice there's a space in front of the equal sign. You want to delete that space. And when I delete the space, watch what happens. Equal average NSE. So it's going to calculate the average NSE value. I'm going to come back to this one. I'll delete the space between the left side of the cell and the equal sign. This is going to calculate the median. The median is the middle value of NSE, and it's 16. Do that for the mode. And notice I used mode.molt. Now, there might be multiple modes when we're dealing with integers. When we're dealing with integers, min and the maximum aren't too far off, and we have a relatively small sample, a total of 60 numbers. It could be the case that we have multiple modes. When we're dealing with numbers with decimal places, multiple modes probably aren't going to happen. And a mode is the value that happens the most often. So when we're dealing with integer data, we need to check for multiple modes. And that's what this does, mode.molt. I'm going to drag molt mode over here. I'm going to highlight several rows. I'm going to come up here and I'm going to delete the space to the left of the equal sign. When I do that, this turns blue and then it highlights the numbers in column A. And then I'm going to press Control Shift and Enter. If I have multiple modes, then you might see 2 or more different numbers here. Because 16 is repeated, I have 1 mode. If you see 3 distinct numbers here, you have 3 modes. If you see 2 distinct numbers here, you have 2 modes. I have 1 mode. So I'm going to come up here and type 1. So now what I can do is I can undo this by hitting Control Z. I'll bring this back over to here, and I'll get rid of the space between the left side of the cell and the equal sign, and I'll just press enter. Again, I only have 1 mode. If you have multiple modes, put in the smallest one. For the standard deviation, I delete that space. It's going to calculate the sample standard deviation of these values, and I get 4.898864. To get the sample variance, delete that space. It's going to calculate the sample variance of the numbers in the blue box. The var.s is for sample data. There's two choices. var.p would be the situation where you have the entire population. Rarely do we use var.p. Most of the time, almost all the time, you're going to use var.s because you'll have sample data. If you have thousands of observations, numerically, there's not going to be much different between var.s and var.p. Now, notice that the variance is just the square of sample standard deviation. These two are the same number. So you don't really need var.s. Now, we don't work with the variance in general because if the units are, say, dollars, the mean's in dollars, the median is in dollars, the mode is in dollars, the variance would be in dollars squared. The standard deviation would be in dollars because it is the square root of the sample variance. So the variance is only really necessary if, well, we're doing a hypothesis test, which we're going to get to. It's a means to an end. We take the square root of it to get the thing that we want, the standard deviation. Next, we're going to calculate the kurtosis. If it's 0, means the shape of the middle of the distribution is going to be roundish. If it's highly positive, you can think of it as a carrot. It's going to be pointed. If it's negative, it'll be really flat. My kurtosis is not 0, it's positive. The center of my distribution probably is shaped kind of like a carrot. The skew is going to tell us if the distribution is skewed left, skewed right, or symmetric. We have a skew close to 0 that's positive. So our right tail is either going to be longer or taller than the left tail of the distribution. If this were negative, the left tail of the distribution is going to be either taller or longer than the right tail. The minimum is found by doing equal min, parentheses NSE. Our minimum value is 3. This value 3 is right there. It's the reason why this frequency is 1. 3 is the only number between 2 and 5.5 in this variable. The maximum value is found by doing equal max, and it is 30. It's why this is 1. There's only one number between 26.5 and 30, and that's 30. And that's why that is 1. Because I have the maximum and the minimum, I can calculate the range. And the range is just the maximum value minus the minimum value. I'm going to highlight the word max, and I'm going to click on the cell containing my maximum value, 30. And then I'll highlight the word min, and I'll click on the cell containing my minimum value, 3. And that gives me a range of 27. The range, variance, and standard deviation give us an idea how much dispersion we have here. The sum is just the sum of the values. Deleting the space to the left of the equal sign gives me the count. And then I want to count the values in this variable NSE, and I get 60. Well, now that I got the count, we call that N, the sample size, and I got the variance, VAR, I can come up and get the standard error. And the standard error is the square root of the variance. I'm going to highlight the VAR and click on the value of the variance by clicking on cell F19. I'm going to highlight the N here and then click on the value containing the count, the sample size, which is 60. And my standard error is 0.632441. Now it says up here, we need how many decimal places? We need 3 decimal places. So I'm going to change all these to 3 decimal places. I'm going to type them in here to make sure I got them correct. So the mean is 15.633. That's pretty close to both the median and the mode. I mean, this is going to happen if the distribution is relatively symmetric. And we've concluded that the distribution is relatively symmetric because our skewness is close to 0. All 3 of these distributions would have skews equal to 0 because they're symmetric about this center line. However, the kurtosis is different. In Excel, typing equal curt, you're actually calculating the excess kurtosis. So this one would have a kurtosis of -2. This one would have kurtosis close to 0. This one would have a positive kurtosis. When you think of kurtosis, think of a carrot, something that has a sharp point to it. The larger the kurtosis, the sharper the point. My kurtosis is positive, but not greater than 1. So it'd probably look something between these two. The range is 27. When you compare that to the mean is 15.633. The range is 27. So these three represent the center of the distribution, and this range gives you how wide the data is, the dispersion. The variance kind of gives you the same thing. When dispersion is large, when there's lots of variation, the range, the sample variance are going to be large numbers. When the data is pretty consistent and close to being constant, these numbers will be closer to 0. The standard deviation and the range are in the same units as the mean, the median, the mode, the minimum, and the maximum. The standard error is the standard deviation of the sample means. Here we took one sample of 60. Now each one of us has a different sample mean. Your sample mean is going to be different than mine. Your classmates are all going to have different sample means. So we could have like 40 different sample means here. Those sample means are going to be pretty close to each other. Unlike the data, which is spread out much further. This spread in the data, the actual observations, is going to be much greater than if we were to compare our individual sample means. And that's why the standard error is smaller than the standard deviation. So the standard error is the standard deviation of our sample means being plural. And standard deviation is the standard deviation of the observations. The maximum is 30. The minimum is 3. The sum is 938. If you divide this by 60, you get the mean. I'm going to press enter and make sure I got those right. Let me show you a little something to help you understand what's going on here. I'm going to order this data. I'm going to highlight it all. I'm going to sort it from smallest to largest. Remember, there are 60 values in this variable. These are the first 30 right here, right? I'll put them in a gray box. And then the last 30, I'm going to put them in a light blue box. The minimum value is 3. So I got 30 here. And I got 30 here. The maximum value is 30. Is there a middle number? There isn't a middle number. The median here is the average of the two middle numbers. So 16 plus 16 divided by 2 is 16. That's why the median is 16. The percentile function is going to be used to find the 50th percentile. The 50th percentile is the number that separates the bottom half of the data, the stuff in gray here, from the upper half of the data, the stuff in blue. The percentile is going to be the same as the median. I can compute it right here. We'll call it the 50th percentile. And I'm going to use this function to compute it. Type NSE, double click. And what is the K? NSE is the array of numbers. Array is just another name for list. K is 50%. The 50th percentile equals the median, 16, which should make sense. The second quartile is found using this formula. I'll type NSE here and then double click on the name of the object. And here, all you gotta do is type a 2 for the second quartile. And notice what it says here. The first quartile is the 25th percentile. The second quartile is the median value, or the 50th percentile. The third quartile is the 75th percentile. So I'll press enter and we'll get 16 again. There were 30 in the gray box. So there's 15 numbers in the first quarter of the data. There's 15 numbers in the second quarter of data. There's 15 numbers in the third quarter of the data. And there's 15 numbers in the final quarter of data. The 25th percentile would be the average of these two. The first quartile would be the average of these two values. The 75th percentile would be the average of these two values. The third quartile would be the average of these two values. The value for the 90th percentile identifies the values that are in the top 10% and in the bottom 90%. So we could actually do the 90th percentile here. The 90th percentile of the variable NSE, comma, 90%. So 22 or higher puts you in the 90th percentile or top 10%. The z-score might be the single most important concept in statistics. And the z-score is just found by subtracting off the sample mean, and then from that difference, dividing by the standard deviation. X bar is the sample mean, S is the standard deviation. And remember what I said about their units. If X is in terms of dollars, the sample mean is in terms of dollars, and the standard deviation is in terms of dollars. So what the z-score does is it transforms this variable so that it has a mean of 0 and a standard deviation of 1. Z-scores of different variables can be compared because both transformed variables will have mean 0 and a standard deviation of 1. So if one variable is dollars and the other variable is miles, you can't say 14 miles is as common as $2. But if you take those two variables, you subtract off the mean, and you divide by the standard deviation, if $2 has a z-score of 1 and 14 miles has a z-score of 1, then the 14 miles and the $2 are equally likely. You can compare them once you've computed their z-score. You really can't compare dollars to miles until you have standardized them by converting all those values into z-scores. So the z-score of NSE equals 17 is what? Where is NSE equal to 17 at? I have 3 instances where NSE is equal to 17. So what I'll do is I'll go ahead and calculate the z-scores right here. For every value in our data set, there's a z-score. And the way to calculate the z-score is to take the value of the variable, subtract off the mean, and then divide by the standard deviation, S. Now, when I drag this down, I want to hold the red box in row 14, and I want to hold the purple box in row 18. I'm going to put a $sign in front of the 18 and put a $sign in front of the 14. And I'm going to press enter. 3 has a z-score of negative 2.57. I'm going to reduce this to 3 decimal places. After I've ordered the variable from lowest to highest, notice the z-scores are getting closer and closer to 0. 16 is pretty close to the mean. The mean is 15.633. 15 is also really close to the mean. 16 is closer. So if I ignore the negative sign, the z-score of 16 is smaller than the z-score of 15. Now, as I compute z-scores, watch what happens. They are increasing in value. 30 is the maximum value. It has a z-score of 2.933. 3 is the minimum value. It has a z-score of negative 2.579. 3 is less extreme than 30. 6 is more extreme than 24 because we're looking at the absolute value of the z-scores. Because 17 is close to the mean, the z-score is 0.279. Now, because it's positive, 17 is greater than the mean, which is the case. That makes the z-score positive. So it implies that net safety events equaling 17 is 0.279 standard deviations greater or above the mean. And I've computed all the z-scores in column B. You want to use these z-scores to compute these percentages. What percent of NSEs are within 1 standard deviation? I'm going to change the font color to blue if the z-scores are between 1 and negative 1. 20 to 11, their z-scores are greater than negative 1 and less than 1. So how many of these are within 1 standard deviation of the mean? I'm going to count them if their z-score is less than 1 in absolute value. So how many are there? There's 44. Down here gives me the count. There's 44. Now to convert that to a percent, I have to take the 44 and divide it by the 60, right? And then multiply by 100. And I get 73.33%. Okay, now we want to do within 2 standard deviations. I'll change the color of z-scores that are bigger than 1 but less than 2. I'll change them to red. I'll do that on both ends. For a moment, ignore the negative sign. I'm making z-scores less than 2, greater than 1, ignoring the negative sign, red. How many are within 2 standard deviations? 6 z-score is 1.966 in absolute value. That is less than 2. So 6 is within 2 standard deviations. 24's z-score is 1.708. That's smaller than 2. So how many do I have that are within 2 standard deviations? I have 58. 58 were within 2 standard deviations. What's the percentage there? 58 divided by 60 times 100. 96.667. How many are within 3? In absolute value, this is smaller than 3. That is smaller than 3. So all of these are within 3 standard deviations of the mean. So I'd say 60 here. So this is just going to be 100%, correct? 60 divided by 60 times 100 is 100%. Now I want to create a histogram and an ogive for this data. A histogram is going to look like that, and an ogive is going to look like this. Now, since I have the original data, one way to create this histogram is just to highlight it and then click Insert, Recommended Charts, and All Charts, Histogram. Click on that. The problem is my frequency table up here has 1, 2, 3, 4, 5, 6, 7, 8 intervals. Here I only have 1, 2, 3, 4, 5, 6, 7 bars. So what I need to do is I need to increase the number of bins to 8. If I increase the number of bins to 8, I get a distribution that looks like this. Now that doesn't really look like it's normal. Notice that my numbers here are different than these numbers. So this is not the histogram for this frequency of data. So that's one way to make the histogram. Another way to make the histogram is to use the upper limits, press and hold the control button, and then highlight the corresponding frequencies. Then you can release the control button. Then you can click on Insert, and then you can choose a bar chart. Notice that this is the upper limit of that interval. 9 is the upper limit of that interval. 12.5 is the upper limit of that interval, etc., etc. This is not a histogram, though. The histogram, the bar width matters. We need to get rid of the gap and the overlap. I'm going to just make that 0. Now I really can't see the bars here. So what I'll do is I'll put a border around it. There you go. So now I can see the bars. This value here is 5.5. This value here is 9. This value here corresponds to 12.5. This value corresponds to 16. Right? So that's kind of like the best you can do with a histogram in Excel if you make it from the frequency table. Now notice how much different it looks than the one that Excel created. They both have 8 intervals, 1, 2, 3, 4, 5, 6, 7, 8. But look at the shape. This one, you may be able to argue that it kind of looks normal. This one, it's pretty obvious that it's not normal. The fourth bar is the peak bar. The third bar over here is the peak bar. And it has to do with the beginning point and the width of these bars. This value here is 2. So this is 2 to 5.5. This is 3 to 6.375. Excel's using the minimum value to define the first number of the first interval. It's using the maximum value, 30, to be the upper limit of the last interval. And that's why these two shapes are different. This is why statistics is so difficult. If I use this, I can make an argument for normal distribution. This makes it look like it's not a normal distribution, but it's the same exact data. And the ogive is just highlighting the upper limits of the distribution that you created, holding down the control button, and then highlighting the cumulative frequencies. And you come up here to Insert, and you pick Scatter Plot with the dots and the lines. And this does look kind of S-shaped, which is what you want. It constantly increases. It does bump out in the middle, and that's because you have this sharp peak right here, and it drops off dramatically. This ogive, though, you might be able to say it's maybe normal, but this is awfully flat, and this sticks out probably too far. But I would say with randomly sampled data, That's an ogive that would suggest maybe normal. This is a histogram that would suggest normal. This is a histogram that would suggest not normal. Now, with regard to the within 1 standard deviation, within 2 standard deviation, within 3 standard deviation of the mean intervals, if it was a normal distribution, it's about 68%. This is about 95%. And this is nearly all. Well, 100 is more than nearly all. It is all. 96.67 is pretty close to 95%. 73% is a little high, but 68 rounds to 70, 73.3 rounds to 70. So these kind of look off, but they're not that far off. These are pretty close, and these are pretty close. So if I were looking at the within 1, within 2, within 3 standard deviations of the mean interval, I'd probably conclude it looks normal. The kurtosis is a little too high. I'd like to see this smaller. And it's high. Why? Look how sharp that is. That's pretty sharp. If you ignore this, that's a pretty sharp point. So this distribution looks very pointed. The skewness is close to 0, but it's positive. So here's the center of the distribution. This has the same height as that. This is shorter than that. This is slightly taller than that. But you have this extra bar out here. That's why this has a positive skew. Slightly positive skew. So when you're talking about normality here, you have to mention this number should be close to 0. This number should be close to 0. This should be close to 68. This should be close to 95. This should be close to nearly all. And this should look like a bell-shaped distribution. And this should look S-shaped.